Hi, everybody. Welcome to another exciting embedded controllers class. Hopefully, people were able to make it to the lab yesterday. I thought that was a very fun lab. What we did was we took this SPI DAC that was built into the audio shield, and we started to use it to synthesize waveforms. In Tinkercad, we don't have an SPI DAC. And I've been looking around, and it seems as though the easiest way to implement a DAC is using the so-called R2 ladder. So in our last exciting microcontrollers class, we used an R2 ladder and parallel output. And to drive the parallel output, we wrote directly to the data direction register, saying everything would be used as outputs. And then we took the value and wrote it out to port D from a sign table. The sign table was initialized using this little init function, and because we're doing an 8-bit D to A converter, we multiplied by 120 times whatever the value is in this parentheses. It'll probably range from something like 0 to +2. And so as a result, we ended up going out to perhaps 240. Can people hear me okay?
Yep.
All right, something's wrong with my setup. Just going to quickly change it. Oh, there we go. Couldn't hear myself for some reason. Let's just open up the sound preferences and make sure things are working properly here. So input should be the Samsung testing. That looks right. I don't know why it's not louder, but just crank the volume, I guess. Yep, that's working. All right. So then when we ran this, I added a little oscope for the output, and then I manipulated the frequency by changing the index into the wavetable. And that was how we proceeded to create the sine wave with different frequencies. And you can kind of see what the frequencies are if you zoom in here and you say, aha, this is 10 milliseconds. And then you figure out that, well, from this trough to that trough is about 10 milliseconds. So that's 10 1,000ths of a second. So
10
10 goes into 1,000, perhaps 100 times. So that could be a 100 hertz output, at least in simulation. And then if you wanted to speed things up a bit, let's see if we can do this. There we go. Now when you zoom in, I think you can change the scale. And perhaps we can go down to
it's 1 milliseconds per division right now.
Yes,
so, yeah.
I see that. But this says, oh, that's 10. Time per division, that must be 10 milliseconds per division. Let's try 0.5. Enter. Oh yeah, there you can get more. Little. So if that's half a millisecond per division, then that's perhaps
3 squares half.
Perhaps a half a millisecond is 1/2 of 10,000 or 1/5000th. Oh, but then it says 5 milliseconds down in here, doesn't it? 5 milliseconds per division. So that's very interesting. I'm not quite sure how this correlates with one versus the other, but if it's 1 division is equal to 5 milliseconds, then that's 5 1,000ths of a second, and 1,000 divided by 5 should be perhaps 200 hertz.
I think the 5 is for the whole grid. The whole grid is 5 milliseconds.
Oh, you might be right about that.
Yeah.
Okay, that makes sense, actually. If this whole grid is 5 milliseconds instead of 5 milliseconds per division, then let's see, 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. Yes, that makes perfect sense. That makes perfect sense. So then it's half a millisecond in the simulation. I mean, it's only a simulation anyway. So with half a millisecond of the, you have 1/5000th of a second, so perhaps 5 kilohertz. Oh, that's a big difference, isn't it? So yeah, that's quite interesting. I didn't realize they were. That's a very peculiar way to represent an oscilloscope, but I guess that's what they want to do. So that's what they do. Such as it is. So looking again at the code, let's see if there were any questions about the code at this point. So it should be pretty clear now. The data direction register is being set up with all outputs. And then to set the port D on the sign table, which is this port right in through here, pins 0 through 7, we just assign it port D equals, and then that'll change the output. And so that's kind of cool. What you want to know in order to know how the ports are mapping to different pin numbers is you want to do the Arduino pin port mapping. So if you ever have a question about how that works, you know, you can use Google. That's probably the easiest thing. I mean, you could read the data sheet. That's good too. But if you wanted to know the Arduino Uno port mapping, I've already done this search once before. You can proceed to see that on the Uno, it's one thing, and if it's on the Mega, it's something else. And it's all because of the number of pins available on each variant of the Arduino. So they're all rather different. And here's an example of somebody doing just what we were doing here. Let's go back to this other reference. I think the reference is what you want. And so here he tells you port B is pins 8 through 13, port C is the analog pins, port D is 0 through 7, and you have to set your data direction register, and then he gives you an example which comes in right over in here. So here he sets the data direction register without manipulating the least significant 2 bits, because those are supposed to be allocated to transmit and receive. And if you do that, sometimes nasty things happen. So that's a inclusive OR. Sometimes you see this instead of DDRD equals DDRD inclusive OR, and then the bit stream, you can say inclusive OR equals as a single thing. So it'll typically be something like this: DDRD bang equals B 1111111, something like that. And so the bang equals is going to set the bits, and it'll be just the same as saying DDRB equals DDRB D with an inclusive OR. So it makes it a little bit easier to read, maybe. So that's, you know, pin mapping is one of those things you're going to have to look up from time to time until you get used to it. So that's the code, such as it is, and that gives us kind of catches us up from where we were last lab. Now I noticed some people didn't attend the lab, so I did record it. It is available. A shortened version, anyway, is available, and it's over in the microprocessors section. And if you scroll down to lab 06, you should see yesterday's lecture has already been posted. And there it is on synthesis. 2020-10-07 is yesterday, and we used the software oscilloscope for that. And there were some questions about how to set up a software oscilloscope. And then we said, geez, you know, this is causing all kinds of distortion. Our square waves don't look square. That's kind of a problem when you use a speaker and a microphone to couple outputs and inputs. If you want to do it upright, you need a cable, and then you wire it to an oscope, And so what I did was this morning I ordered a whole pile of cables for the lab so that we can hook things up directly to our scopes in the lab. So that'll, make a difference for people who, want to use an oscilloscope. For those individuals that don't have an oscilloscope at home and they want to do this at home, I'm astounded by how cheap little oscilloscopes have become. And so if you wanted to, you can find very inexpensive oscilloscopes on Amazon. To me, this is amazing because I used to spend real money on oscilloscopes, and now basically they don't cost anything. So you might as well get one for yourself if you really want an oscilloscope. You don't need a particularly fast one. So if you just do oscilloscope and then filter by price. Let's see if I can do this. Sort by price. He won't let me. Low to high. And let's see if we can get an O-scope in here. Because I saw a nice portable one, and it was, I don't know, it was less than $20 or something, really inexpensive. It had the look and feel like, here's something that looks like a real O-scope. 100 megahertz bandwidth, giga samples, $141. I was like, whoa, that's cool. And then they have these little do-it-yourself O-scopes. And they give you the case, and then you can sit there and make one for yourself. And here's a little one for $86. I mean, these pocket scopes look so cute. $100 for a scope. Can that work? I don't even know. Here's one where, I mean, is this even believable? Now, it's only 11 mega samples per second. It's basically like a little Arduino with a touch screen, but somebody has turned this into a kit, and I guess you'd have to sit there and solder it. And then what? You have an $11 oscilloscope? How good could that possibly be? I don't know. Got to read the reviews on that one. $11 is an unbelievably low price. Too good to be true. And then there are these cases which you can buy for it. And here's one for $81. It fits in your pocket. I mean, it's just mind-boggling to me that these scopes are so cheap. So if you're at home and you want to do this at home, we can't supply you with a scope, but if you decide you want to supply yourself with a scope, here's a mini shell. I don't know. Got to shop a little bit. Here's an acrylic case for the little scope that we saw. That brings the price up to $25, I guess. And here's a mini scope already assembled, which is probably worth it. $125. Wow. So there it is. Scope shopping. I just think that's amazing. You can get the used scopes also very inexpensively, but these are new. So, I mean, wow. So let's go back to some of the content that we were going to have to deal with. Today, we have a homework. And what's due today is homework number 5. And what I thought I would do is ask if you guys had any questions about homework 5.
Yeah, one sec.
Homework 5 is the SPI DAC. It looked like 20 people have already tried it. And so, one thing you can say about the SPI is it's extraordinarily fast. It's full duplex. The serial clock is for the actual SPI interface has a minimum of divide by 2 in the prescaler. So for our little 16 megahertz Arduino Unos, it'll probably be running at about 8 megahertz, which is about as fast as that Arduino is going to be able to take any data anyways. But if you had a faster computer, SPI will run faster. And if you have a 64 megahertz clock in your little CPU, this thing will probably run at 32 megahertz. And so that's not nice. The basic limit, of course, is that you've got to select every single device. So your master will always be the CPU and the slave will always be some device, and you can't go faster than the device can take. So that's a basic fundamental limit. That's the serial clock input for your device. And you can find out what the limits are. Here's the data sheet for the MCP 4921 DAC, and you can see it's got a serial clock input here. And so there's going to be a spec on the max. We don't go anywhere near the max. And in fact, you don't want to operate at the max, because if you're a good engineer, you're going to try not to push the limits of what your device can handle. There's also a little protocol thing that goes on with the LDAC input on these things, which essentially do a latch transfer from the internal DAC to the output latches. And so LDAC has to be asserted low in order for that transfer to occur. And so first thing you do is you shift the data in, then you assert the LDAC low, and that gives you the ability to output to your serial device. I've glossed over those details basically in the driver, because it doesn't really add anything to the lecture, and it's one of those things where you got to read the manual pretty carefully in order to get these things to work properly. And then of course the pin changes if you change device. So this is a monophonic DAC. There's also a stereophonic DAC, the 4922, which I could have used at very little incremental cost, but didn't, because my little Arduino doesn't keep up so good with stereo. But if you look at the difference between the chips, you can see the chip is almost double in size. Right, we go from an 8-pin to a 14-pin DIP, and it's available both in the parallel DIP and a small outline integrated circuit, and in other packages too. And so this is a reference to what's called the surface mount device, and there's some details that go with that. If you're looking over in here at LDAC, here's LDAC right here. LDAC is going from the input register, which is being populated through the serial clock and serial data in. So that's like a shift register. Once the shift register's got all its bits lined up, then LDAC comes in and lets the shift register go through to the DAC register. And then that's when you get your output. So LDAC is one of those critical synchronous things that you do after the SPI interface is done populating the register. So I thought I'd mention that because you're going to see LDAC in the code, and that's what it's there for. That's what LDAC is all about. And you can find that in the Arduino code. You'll see LDAC being asserted when you're doing an SPI DAC transfer. So that's that. Let's see, what else can I tell you about this? The rest of it is kind of like details. This thing takes microamperes. It's got very high resolution, 12-bit resolution. It's just like a nice DAC for what they give you. Any questions about homework 5? I know you were going to look it up.
Yeah, I think Ali is asking for number 6 on the chat, but I was wondering if we could go over 18, 19, and 20.
Sure. Let's do that. Just wanted to see if 18, 19, and 20. I think we have to click on it to get this to show. Oh, I have to click begin. Oh, we had some issues with the images from last year. They didn't carry forward. So I went through and I carefully edited the questions so that things would be more clear. You wanted 18, 19, and 20 from homework 5, right?
Yes.
18 is, you can sort of see I put in a few more things into 17 because it wasn't clear last time. And then 18, in the following code. So here's the actual Dac code, which I think should be the same code as here. So this is doing SPI transfers. It's pulling the chip select low, putting the chip select high. That chip select is like your LDAC. Here it is, LDAC low. That must be bit 0. Let's see, what is he doing here? Pull LDAC high. Yeah, so he goes from low to high. So you can see LDAC is doing a transfer. And then over here, it looks like I've reformatted the code just a little bit so it's more in line. Then it says, which of the following answers seems most correct? Consider. Okay, so here comes the port mapping question that we were just looking at. So if you were looking at port mapping for pins B, C, and D, you would see B goes from pins 8 through 13 on the Uno. Port C is your analog input pins, and port D is pins 0 through 7. So then somebody says the data direction register D is going to be 1, 1, 1, 1, 1, 1, 0. So it looks like Arduino sets pins 1 through 7 because D is ports 0 through 7. So it sets them as outputs because they're all set to 1. Right? It says pin 0 as an input. That looks right. And then you can also say something like this, DDR equals DDR, or this is safer because it sets pins 2 and 7 as 2 through 7s as outputs and leaves bits 0 and 1 alone, which correspond to the transmit and receive line. And you don't necessarily want to muck about with that. And so this says output buffer is equal to 0, 1, 1, 1, and then all the rest are 0. Sets the most significant 3 bits to 0. It doesn't, right? Because it's only the most significant 3 bits would include that bit there, but that's a 0, so that's not true. Then this says it starts pin 9 to 0, and what do we see about port B? It's 8, 9, 10, 11, 12, 13. So this is going to be 8. There's pin 9, so pin 9 is 0. So that seems true. And this says asserts pin 8 to low. Well, that first pin is 8 for port B because port B starts on pin 8. And so that must also be true. And so the answers are 2 and 3 are correct. And maybe you could see why that's true because of how the pin mapping goes. And not to put too fine a point on it, but if you wanted to, you can always get the pin mapping for the Arduino Uno. Oh, they have a nice PDF file here, I guess. Well, that's the pin mapping for the 168. It's probably the same. Oh, well, here you go. So now you can see port D, port B, and port B0 corresponds to digital pin 8. That's the confusing part, right? So here's pin 14 on the chip. That's port B0, and that is going out to digital pin 8. Port B1 is somewhere.
Right next to it.
Here it is. Yeah, it's over on the other side. So there's pin 9. Port B2 is 10. Port B3 is 11. Port B4 is 12. You can see the conflict with MISO and MOSI, right? Here's the serial clock. Port B5, that's pin 13. So it's pretty clear. If you start using port B for other things, you're MISO, MOSI, and SPI interface may not work properly. So you got to be careful about that stuff. There's a contention issue. So this actually is a very nice and condensed port mapping, and even though it says at mega 168, the 328 has the same port mapping. And actually down in here it says pins 11, 12, and 13 are used for the in-circuit system programmer header for MOSI, MISO, and serial clock connections. Avoid low impedance loads on these pins when using the ICSP header. I've never had this problem, but that's probably why certain things didn't work, right? That's a gotcha. Like you got to read the directions or something. So that's an interesting question and a good one. Very good question. Hope that answered your question.
Yes, thank you.
Good. So then here comes question 19. That was on the list. And now this is an analog to digital converter question. And what is the role of ICNT? Now, ICNT, it sounds like it's a index counter for this DD array, whatever the DD array is doing. Let's see. So the index counter is being incremented by one of the ADC bytes. We increment it by 1, and then that will allow us to jump around in the jump table. And instead of checking to see if the index counter is greater than 511 and setting it to 0, in case it is greater than 511, what we did was we ANDed it with 511, and that effectively limits it. So once it reaches 511, 511 and 511 is going to give us all ones. Why would that be good? Sounds like a rollover. That doesn't sound right. That looks weird. But anyway, what's the role of the I counter? And it looks like it's going to alter the frequency of the tone. It is an index to the wavetable, and it is sampled from the ADC. So that kind of looks like it's an all of the above kind of thing to me. What do you think of that? I can always check my answer key just to be sure, but all of the above is the way I would roll on that one. Let me see if I can bring it up on my other screen. Things just seem to slow down when Zoom is sitting around recording. So we're on homework 5, and I think is that the last question?
Number 20.
No. Yeah.
There is a number 20?
For
All right,
21, when we get there.
You want to do 21 too? All right, so let me just take a quick look at the answer key on this just to make sure I got it right. This is number 19, I think. And what is the role of the ICNT? Index into the wavetable is the answer that I am showing. I guess you wouldn't say it's to sample from the ADC because it's really the sample plus 1, so it really is an index to the wavetable, so that's all right. Alter the frequency of the tone. I guess it doesn't directly do that. Indirectly it does it because it's jumping around on the wavetable. So I guess the best answer in this one is index into the wavetable. That's for sure. So the other stuff, maybe not so sure. What else we got in here? 20. So 20 is using the timer counter overflow interrupt enable register. Boy, that's a mouthful. Timer overflow interrupt enable. So what's going on with this thing? There's a piece of hardware which can run at the same speed as the CPU clock. It can run at a maximum of 16 megahertz. And what you can do is you can have it generate an interrupt. And when the interrupt comes in, you can service that interrupt. And that's the sort of an interesting internal clock that you can essentially set to an arbitrary value. When it reaches the overflow, it interrupts, and then you can service the interrupt and reset the timer and set it so that it'll interrupt again. So then it says here, blah, 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 documentation. Now it says here comes the TIMSK0, which is this register. And what he's saying he wants to do is clear the bit that corresponds to TOIE0. And TOIE0 is the least significant bit. And it says here bit 0 is the timer counter 0 overflow interrupt enable. When TOIE0 bit is written to 1 and the I bit in the status register is set, the timer counter overflow is enabled. The corresponding interrupt is executed if an overflow in the timer counter occurs. When the T0V0 bit is set in the counter interrupt flag, TIFR 0. So disable timer 0, delay is now off. I think that's clear. This has to be enabled. This has to be set. So I would use SBI if I wanted to turn the timer back on. Okay, that sounds fine. And so what's the question here? There's got to be like a question in here somewhere. Oh, here's one. SBI TIMSK 1. Which one? Oh, that's this one. And he wants to set bit 0. No, he says he wants to set, bit 0. So bit 0 of TIMSK1, which is the TOIE1. So TOIE1, that's the timer overflow interrupt enable when the counter wraps. So this is enabling timer 1 and disabling timer 0. So that, I guess that's what this is saying, right? So he's saying by clearing the least significant bit on timer 0, we turn it off. Now we're going to set the least significant bit in timer 1, and we're going to enable interrupts on timer 1. I like that. That's sort of fine. So now it says here, what are my choices? Here's something about prescalers. Here's interrupt frequency matches. Enable an interrupt set request invocation whenever the timer reaches. Reaches. This doesn't sound correct to me. It's not decent English, is it? It should say reaches its limit. Whenever it overflows, it should say. Reaches its limit. That's true. Enables an interrupt frequency which is equal to the Arduino clock speed of 16 megahertz divided by the prescaler times the compare match register plus 1. Now that's true. And I think you can get that if you read the documentation in here about timer frequencies. If it isn't in there, it should be. Or perhaps it was in a different section when we talked about timer frequencies. But if you want to know how fast it interrupts, you basically need the prescaler in here, the compare match register, and then you add 1. So this is an example. An example. That's very fine. So frequency of 1 hertz says a prescaler times 1 hertz and then divided into 16 megahertz with a prescaler of 1024, you get 15,624. And since 15,624 is between 256, which is an 8-bit timer, and 64K, which is a 16-bit timer, you must use timer 1 for this interrupt because timer 1 is our 16-bit timer. Timer 0 is an 8-bit timer. That's why we're disabling timer 0 and using timer 1. That's
so it's all the above?
Yeah, I think so, because why? Well, because I need the 16-bit timer, that's for sure. And this tells you how to get the frequency of your interrupt, which is really good, actually. You need that. So you figure out what kind of a prescaler you're going to need, because, you know, your temptation might be, oh, okay, let's just make the prescaler 1, and we'll have a precision equal to 116 megahertz of a second. But that doesn't really work because your counter can't count up to 16 million. It can count up to 65,536, and that's it. So you've got to prescale the 16 million to get to a number that's reasonable for the comparator. When the timer counts up to the 15,624 at the prescaler rate of 16 million divided by 1,024, then it will hit the trigger. So timer frequency is going to be something like 16, 1, 2, 3, 4, 5, 6. I'm using a calculator now, divided by 1,024. So the actual timer frequency is 15,625. And so what you do is you put in 15,624, adds 1 to that, because as soon as it reaches it and overflows, it triggers the interrupt. And so that's why this timer is actually running at a frequency of 15,625 hertz. So you take that frequency, subtract 1, and that gives you the compare match register. So when the timer reaches that frequency, that number, it triggers the interrupt. That's cool, right? Because if we can know that, then what we can do is we can program our timers to let's see if I got an example here in my Tinkercad. Because we want to program our timers to blink and do things and whatever. So here's the blinky light, right? We've done the blinky light before. We're going to do it again, only with a difference. And the difference is we're going to go into the timer control register, right? And so now with the timer control register, using timer 1, we have a 16-bit register with timer enable. And now we can make an interrupt service routine out of blinking the LED. And so then, this is what it did anyway when we did a delay. Only now we can do whatever we want to in the loop, even nothing at all. And this will wake up every second, and it will read what's in the present digital pin, use exclusive OR to invert it, and then write it back out. So in principle, this should blink, I hope, and it does. Look, light goes on, light goes off, goes on, light goes off. So you can have fine-grained control of the timer and then control certain things that go on in the background, while in the foreground you can have your loop running. So in the background, what you could have is your ADD converter pulling in samples, running it through some process, and then in the foreground you can do some kind of, I don't know, fancy thing, whatever that is. So that's a good example of how you might use the timer to do something like make the light blink. You probably want to do other things with it than that, but there it is. So that's a good one. Let's see, question 21. I guess you didn't ask about that. Perhaps you guys
Can we
know
do it
already.
anyway?
Oh, sure. Let's see. Match the description and image that makes things seem most correct. Most correct. What the heck is this? Let's see. I've got an ALU, a control unit, data memory, instruction memory, an IO. Oh, I see. You have to do each one is separate. A is von Neumann architecture. B is Harvard architecture. C is Harvard architecture. And D is memory mapped IO. Okay. So what do we know about Harvard architecture? We know that memory for data is separate from memory from the program. And it looks like if you have instruction memory and data memory, that's kind of like Arduino architecture. So that's Harvard architecture, which is...
Why is there two Harvard architectures?
Yeah, there is two Harvard architectures. I see that.
And I think if you choose one of them for the other one, and
Yeah, you get it wrong.
yeah, so it's kind of a weird question to answer. I don't know how to.
Well, this
There's
would
no
be
do them
on
in order.
Neumann
The
style.
first Harvard
Okay.
architecture one is the first selection for Harvard architecture.
Yeah, I think if this is Harvard architecture, then what is the next one? RAM and ROM. ROM could have your, this kind of looks like Harvard architecture to me too. And then what's the next one? Microcontroller has RAM and ROM, but it has I/O ports. So what's this I/O port about? That I/O port,
Probably D.
yeah, that's looking like, to me, it's looking like a, what's the term? Memory mapped I/O. Was this a buggy question because there were two Harvard architectures?
Well, it
Oh.
works, but you have to do it in order.
Yeah, that's not good.
And it just goes A, B, C, D. So
It goes A, B, C, D, but it says Harvard memory mapped I/O. I'm not liking that,
yeah.
but you guys have probably already submitted answers, so I can't change the answer key. I'm going to have to make a note. I'm going to call this a bug in homework 5. Homework 5, number 20. I am going to fix that bug without changing the answer key so nobody will get anything wrong, but I would like to make it a little bit more obvious. But the answer is A, B, C, D in case you haven't done it already. And I'm just going to write that there's a bug and go over that after class to make sure that we don't have duplicate answers. Sorry about that.
It's okay.
Got a bug. So that's homework 5.
Can we do number 6? I asked it in the chat, but it was
Yeah,
glossed
yes,
over.
6. And could we also do 9?
Sure. So let's go back to 6. So this is like a calculator question. I wonder if I can do this calculation on the screen here. 4.5 microseconds. Can Google do that? Let's find out.
Google
Google.
Calculator is great. I use it for lots of things.
So what is the frequency, I love this, of 4.5 microseconds? Can you do that on Google? Oh, convert hertz to microseconds? Convert, I don't know. Can this work? I'm not clear on this. This is not this is not the right calculator for me. Microseconds to seconds, is that how that works? So 2.5, can it take fractions? 2.5 microseconds, is that what we were at, or 25? I forget. 4.5. 4.5. Convert. So that's, yeah, that makes sense. I don't need a calculator for that. 4.5 times 10 to the minus 6. So what I want is 1 divided by 4.5 times 10 to the minus 6. Can this do that?
You multiplied it by that twice. So
Did
that's
I?
a power. Yeah, it considered as a power.
Oh,
The search bar.
oh.
There you go.
So what does that say? 22 kilohertz?
That doesn't look right to me. I don't know.
It doesn't look right. Okay, I'm going to try it on my hand calculator. 1 divided by 4.5.
It's because e to the negative 6 means times 10 to the negative 6. So you just need to do divided by 4.5 e minus 6.
Oh.
Oh yeah, so you took
Take
one
out
of
the
powers.
times
Yeah,
10.
it should be 222
It's shorthand
kilohertz.
notation. Once you put in the e, that it assumes the times 10. So take out the 10 and the multiplication
So
symbol.
that's what
Just
I'm
do
looking
that.
for?
Yep, just that.
That looks right.
222 kilohertz. There you go.
Yeah, I see. This is a calculator I don't know how to use, but you were correct. That's the correct way to do it, and that is a correct answer, 222 kilohertz. That looks like, well, pretty
So you
close.
just changed the seconds to, okay. That was simple.
Yeah, I just went over the period is equal to the frequency.
So
That's-
the sample rate is the frequency?
Yes, frequency is
Yeah, I
samples
mean-
per second.
Yeah, he's right, saying the settling time for this DAC.
What is settling time?
I'm wondering if that isn't true for this thing, because there are probably I don't know. There's probably something in here called settling time.
Yeah, that is what it is. It's 4.5
Yeah,
microseconds.
there it is. So he's saying that the settling time for my DAC is 4.5 microseconds, which means the maximum rate at which the DAC can go is 222.222 kilohertz. And accuracy is better than 1 least significant bit for V out equal to 10 millivolts. Blah, 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 within 1.5 least significant bit of final range from blue, and crosstalk. So basically, you're going to have 12 bits of signal to noise ratio, which is probably 6 times 12 plus 3 dB. That's about 75 dB of signal to noise ratio maximum on your output, assuming you use all 12 bits. So that's a that's consistent with the DAC that we're using. Don't know if you're going to actually achieve that with what we're doing, but you know, there it is. That's in theory best you could do. What was the other question, please?
Question 9.
Which number?
9.
Number 9.
Yeah.
Let's have a look. Number 9. In the following code, UINT 16, so that's an unsigned 16-bit quantity, and we're allocating 512 samples, and we're going to fill the sine wave. This is very similar to what we did before. This number is going to range from minus 2047 to plus 2047. And so what we're doing is we're going to take the actual value and add 2047 so that it'll go from 0 to 2040, 0 to 4095 maybe. what is 2047 times 10? 4094, I think. Isn't that right? 2047 times 2 is 4094. Our maximum that we can represent is 4096. So this gives us like 2 voltage quanta of headroom. Anyways, having said that, what will the range for DDI array be? And so it's 0 to 2047 times 2. That sounds about right. And that's correct. 2047 times 2. That's how I read it. That was question number 9. I'll check my answer key just to be sure.
I'm sorry, what are the dots?
Bear with me just a minute. Yep, I was correct. The dots, that's a 0 through 2047 times 2. Right? So this is what happens, right? Sine ranges from -1 to +1. 2047 times -1 is going to be minus 2047. If you add 2047 to minus 2047, you're going to get 0. Then it says sine can also go up to +1. So +1 times 2047. If I add 2047 to 2047, I get 4094. And 4094 is 2 times 4097. So that's correct. That's how I read. That's how I read that. I don't know if that sounded confusing. I hope it didn't. But that sort of makes you think about why we're doing what we're doing in here. Because our DAC is an integer device. It doesn't like floating point numbers. It has a fixed point range that goes from 0 to 4095. And so here we have, synthesized a wavetable that goes from 0 to 4094. So that's kind of where that's coming from. What other questions do you guys have for me? Does that sort of cover
Can we do
homework?
7-11?
7? Question 7?
And then 11.
And then 11. What range can, when I see the word can, is able, what can the range be for the MCP 4921? We know it's a 12-bit DAC. Can the range be from 0 to 4095? And the answer is yes. Can the range be from 0 to 1023? And the answer is yes. We can use just 10 bits if we like instead of 12. Can the range be from 0 to 255? And the answer is yes. We could just use the least significant 8 bits. So we have our choices, right? Any of the above. Any of the above. What do you think of that? Does that sound correct? Question 7. I'm looking at my answer key now just to be sure. Yeah, any of the above is correct. I was right. Any of the above. And so then you said something about 11. Was that right? Question 11?
Yeah. There it is. Just couldn't
Okay.
understand what it was asking.
Sure. So now he's asking about the SPI clock, div 8. So what is 16 megahertz? That's our system clock. What's 16 megahertz divided by 8?
2.
Yeah, I guess, right? So that gives us the clock for the SPI interface, and you got to figure that we're always going to divide the system clock by 2, 4, 6, 8, 16, right? That's going to that's going to choose what the SPI clock will be. And the question is, how do we know what to set the SPI clock to? And the answer is, we can't unless we know something about the device we're trying to drive. If the device can't go faster than 2 megahertz, then we better be careful about setting the SPI clock to div 8, because that's really the limit, the upper limit on the device, and you don't want to actually drive these things at the fastest rates they can handle. So if you really want to know what the fastest rate is for your device, then what you need is like the data sheet, which I had here somewhere, but somehow managed to promptly lose.
Find it in your history.
I just thought it might still be open. And maybe it is. Just perhaps it's in the other browser. Just a minute. And there it is. So what you wanted to know was the specification on the SPI clock. And that would be something in here, I imagine. What would they call it?
I believe it's 20 megahertz on this data sheet.
And is it SLK? Serial CLK?
SCK, I think. I think it's just SCK.
SCK?
Yeah, I think on that sheet.
Do Control
Yeah,
F.
Control S, will that let you do a search?
Control
No.
F will be
F,
searching
like
that.
as in
Control
fig.
F? Control F, will that let you see what happened here is
Oh,
it
you're
did
on
a
a Mac.
Google search.
Oh,
So that doesn't actually search the
Command F.
Command F. How do I do that? Wasting too much time on this. I'm sorry.
it's okay.
Perhaps if we said save as PDF and then opened it with something a little bit more rational than the browser. Now I can do a proper search.
Yeah, it is Command F.
Oh, here it is right in the top. SPI interface to 20 megahertz clock input. So he can easily handle the 2 megahertz. In fact, he could handle, in theory, the 8 megahertz if we wanted to go that fast. So that's all there right up front. If you had a number of these DACs, they could all be put into the same bus using chip selects, and then you could run them all at the same clock speed. That's one of the things about SPI. The serial clock is shared among all the devices, so it can't go any faster than the slowest device. But this one's a pretty fast device, so especially relative to our little toaster controller. So that's that. Are we done with homework 5 now? Any more homework 5 questions? That was exciting, wasn't it? Very exciting. So what I thought I would do is show one of these other circuits that I was tinkering with. It's kind of an interesting tinker experiment. And it's
That looks cool.
Yeah, this is a multiplexer. You're like this. So the question then is, how do I drive a lot of LEDs without a lot of output lines? I mean, here's 1, 2, 3, 4, 5, 6, 7, 8. So there's 64 LEDs, right? How do I do it? And the answer is you do it through multiplexing. You scan left to right, and then you move top to bottom. So as you go from left to right, you choose which of the bulbs in this column are going to be turned on. Then you go to the next column and you choose which ones are turned on. Then you go to the first column, you keep going. You just scan left to right and then choose which bulbs in that column will be turned on. Let's start the simulation. And here's a little button over here. And now you've got a kind of an interesting thing going on.
Professor, can you send this Tinker file to your to us or no?
Sure, sure.
Thank you.
It's actually a search. If you want to go on to Tinkercad, you can search, but I can send it the way it is. Sure.
Thank you.
So this is a fancy way to do it, but not very fancy because it's using a lot of wires, and you can see that, right? In fact, one of the things I'd like to do is maybe see if I can change the resistance from 1 ohm to from 1 kilo ohm to 1 ohm. And then what does that do to my speed? Does it change anything? Oh, that's probably just a debound circuit in here. That's not going to change anything. Let's see. What I really want to do is make this thing go so fast that you can see the thing can randomly address an arbitrary LED. But it's using too many wires on output. And I would like to be able to reduce the number of wires that I have on output. And so my example, my next example, which is kind of interesting, and it's very similar to what you would do with SPI, is I use a shift register. So this is a 74HC595 8-bit shift register. And what this does is it hangs on to a data input and a serial clock input. Let's see if we can start this. So you had to add a chip to do it. And you can see it's coming in off of the MOSI and the MISO clocks coming off of here and shifting into the register. And now you can see there's a, I don't know if you can see the lights are changing. And if I click on the button, I can change my pattern. And so this is very useful because if you can imagine, instead of lighting up LEDs, we stimulate the output of an R2 ladder, we can basically simulate an SPI DAC. So if we take these little LEDs and use them as inputs to our little SPI DAC, this enables us to avoid having to use 8 outputs. And in fact, if you wanted to go so far as to have, let's say, a 16-bit DAC, you could have 2 of the 74HC595s chained together and get 16 wires on output, and then use that to drive your R2 DAC. And then you can have as many bits as you like for your DAC.
Can you do it?
This is, go ahead.
Can you do the same thing for inputs? This is only outputs, right?
You can do it for inputs as well. Yes, that is right. You can use it for inputs or for outputs. The DAC is just going to essentially allow you to increase the amount of I/O that you have. Now, there's another way to do it. You could go to an Arduino Mega that has more inputs and outputs in general, and that's a nice thing. But I really wanted to be able to simulate the SPI DAC, and this kind of lets you do that, right? Because a shift register like that, using the serial clock and the serial data in from master in, slave out, master out, slave in, master out, slave in is MOSI. Using the MOSI and the S clock line, you should be able to strobe data in and have it display on your screen like this, or perhaps go to your little DAC. So that's kind of a nice way to go if you don't have an SPI DAC like we don't have here. And that's sort of a bummer, really. I mean, but if you needed a 595, you can actually find one. Here it is. So you can take these things and you can drag them in and build what you like. And that's kind of cool. And you can actually find these very inexpensively on Amazon or eBay, and they're pennies each, and they plug right into your perf board, so you can build little projects with them if you like. So that's very fun. So that's something we can get into a little bit more later. I just thought you'd like to see that because it seems like a nice, it's a nice way to program around the fact that we don't have an SPI DAC. I wrote to the Tinkercad folks and I said, how come I can't create my own SPI DAC? And they said, we don't have that feature yet. And I'm like, really?
At least there's the word yet.
It's just, it's a hobbyist tool. And it's very nice for the hobbyists because you can sit there and you can write code and you can simulate it and it's free and it runs on the cloud. And I think they're just trying to figure things out, So this is a cool tool. I don't want to diss it, but it does have, how can I say, it has blemishes. There's another one which doesn't do the simulation, and it's called Circuit IO. And this guy is just got a lot of cool factor in it. I have been playing with it for quite some time, long before I was playing around with Tinkercad. And so I'll just give you a quick demo on this one because it's got all these different interesting Arduinos in it. And it kind of has a lot of appeal to me, I think. So if you put in controllers and you say something like Uno, it should come up. Yeah, there it is. And now if you wanted to put in your input device, you might have something like a, I think we've done the ultrasonic sensor. Yep, there it is. Take your ultrasonic sensor and drag it in, and it wires it up. That's cool. But even cooler is it gives you a code sample. And that is really nice. And you can use that code sample and play around with it. And here's the other thing, which I think, makes it really, really nice, is if you said, oh, well, you know what? I also need something else. I need a servo to go along with my ultrasonic sensor because I want to scan something. So here's my servo, throw the servo in, wires it up, and now I have code for both the servo and the echo facility integrated. And the only trouble is it won't compile anything and it won't run anything and it's not a simulator. But gee, isn't that cool? It shows you how to lay it out. I mean, how cool is that? And then for the project guide, you can go to the project guide and he'll tell you what the parts are. And he'll even let you order the parts from wherever to go and get that done. So you get a bill of materials, the wire, all this other stuff. So that's very fun. That's a nice way to do quick prototyping, I think. And it has the look and feel of, well, what if I need this? And what if I want this? And what if I want the other thing? You can just keep laying it on. And if you said, well, I don't like the Arduino Uno because it's too big, I want to do something with a micro, go and get a micro, throw the micro on there instead, and it rewires it for a micro, which actually, that puts a lot of cool factor in there because all the pins have changed, the code layout has changed, the pin mapping has changed. He just did a lot of work for you. So I thought I'd throw that out there because you guys can quickly prototype something for your, senior project or your, what was that thing? The boat. The boat needed a motor.
IEEE.
Yeah,
project.
IEEE motor. And that motor was not a servo. It was just a motor, right?
It was a jet motor.
Well, I don't know if you're going to find a jet motor, but there are motors, okay? And there's stepper motors, there's servo motors. Here's a peristaltic liquid pump motor. I guess I could throw that in there. So now I've got a little motor and it throws out liquid. So that's kind of like, I don't know. Oh, and he even put in a little MOSFET that can drive 30 amperes and 60 volts. And he gives you an external power supply. Isn't that cool? A 12 volt, 2 amp power supply to power the MOSFET so that the motor can run. How's that?
That's
I mean,
really
that,
cool.
that just put in a cool factor. And if you say, well, gee, that I don't need this anymore, I'll remove it. That's cool. And you say, oh, maybe I don't need an ultrasonic sensor, although you don't want to bump into things. So that's probably nice to have. And then you might have other kinds of input devices for your, like maybe you want radio control. So if you want radio control with all that, throw in an NRF 24LO1 wireless transceiver that goes on top so that you can communicate with the darn thing. I mean, this just got complicated, right? So now I've got a way to power it from a wall power supply, or maybe one of those lithium ion 12 volt battery supplies. Got my peristaltic pump, a wireless interface, an ultrasonic sensor to keep me from bumping into things, and a controller with a MOSFET. I think I just did, I don't know, a weekend's worth of design in about 2 seconds. So that to me is like, wow, how, that's cool factor. And I think over in here, yep, he gives you the list of parts and even a place to go buy them if you feel like you want to let it buy. I mean, do I really want to go and buy jumper wires for $1.95 each? I don't think so. But that's, he gives you the list of parts and you can go buy them. You can buy an Arduino micro for $25, which is a really good thing to do if you're insane. Right? I mean, who would do that? Well, I guess it's easy if you're on a budget or something. So that's a bunch of code that he gives you, which you may or may not want to use directly, but at least it'll let you test things. And then, of course, he's giving you the wiring diagram and the full project, the so-called firmware, which you'll be able to download and compile. So that's got a lot of cool factor to it, I thought. Isn't that cool? No? Yes? Oh, and you can create your own components in this one. Tinkercad won't let you do that, but this program will. On the other hand, Tinkercad does simulation, and this program does not. But then again, you really can't simulate a complex system like this. You got to test it, especially if you're going to do some kind of RF communication and sensing and driving a boat. And I mean, there's too many things that can go wrong, I think. You got to build the system and test it as a system. So that's what I have for you for today. Hope you like my my little demo here with Circuit.io. I thought that was pretty slick. Any questions about the homework due tonight?
All right. Thank you, Professor.
Okay, then. Well, thank you. Stay safe. And if you're in the architecture class, I will be there in person this afternoon. Talk to you later.
Thank you.
Bye.
Thank you.
Thank you. Bye-bye.
Which architecture class?
I teach computer architecture.
Is that for the electrical engineering, computer science thing?
Yeah, I think anybody can take it as a elective, but I believe it's required for computer science, required for computer engineers, required for software engineers. But I don't think there's too many computer engineers or software engineers left. So electrical engineers would take it as a
Concentration.
an elective. I think biomedical engineers can take it as an elective too. I've never seen a mechanical engineer in computer architecture because digital design 1 is a prerequisite. So if you've had digital design 1, then you would certainly be allowed to take it. The question of whether you can fit it in your schedule or not.
Okay.
That's a whole other matter.
Yeah, we'll see. It sounds really cool. I don't know.
It is cool. It's a great course. I go over all the latest and greatest stuff. Let me stop the recording here, just so that nobody has to hear this. Stop.